All right, welcome back. So we're gonna get back to circling back to linear independence, which we talked about the other day, or I talked about it today. You saw the video, hopefully, the other day. Time travel, whatever. Anyways, I'm speaking to future you, and I'm saying, let's define linear independence for more general situations. So the functions, and we could also think about this in terms of vectors, okay? Because really what we're doing here is we're thinking about functions as vectors themselves, okay? So the functions f1 through fn are called linearly dependent, okay? If there exists constants c1 through cn, okay, not all zero, with c1 f1 plus c2 f2 plus cn fn equals 0. Okay? And if that happens, what that really sort of means, or what that means for us, is that one of those functions can be written as a linear combination of the others. And really, it means any of the functions can be written as a linear combination of the others, as long as the c is not 0. Okay, so if we suppose that Cn is not 0, okay, then Fn equals C1 over Cn F1 plus C2 over Cn F2 dot 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 plus Cn minus 1 over Cn Fn minus 1. Okay, so that Fn is written as a linear combination of the others. Okay, and likewise, okay, the set of functions f1 through fn are called linearly independent if c1 f1 plus cn fn equals 0 only when c1 equals c2 equals all of them are 0. Okay, all right, so before we do examples, let me actually just do a couple that are pretty much, these are very important. So we're going to say that these sets are linearly independent sets. They're important for us. So the importance of linearly independent sets is that linearly independent sets allow us to write any other function sort of as a linear combination of them. Okay, so we use them to sort of, yeah, exactly that. We use linearly independent sets to express our solutions sort of just as a series of them, okay, as a sum of these linearly independent functions, okay? So some important linearly independent sets are, for example, 1x, x squared, x cubed. We could keep going till x to the n. Those are linearly independent, okay? Another one, e to the x, e to the negative x, with e to the 2x, e to the negative 2x, e to the 3x, e to the negative 3x, and we could keep going as long as we want. Okay. And finally, this one's also we're going to be using, let's add 1 in here. Cosine x, cosine 2x. Oh, actually, instead of cosine 2x, let's first put sine of x. Cosine of 2x, sine of 2x, cosine 3x, sine 3x, all the way up to cosine nx, sine of nx. Okay, and if you remember Euler's formula from the other day, you may ask, well, are these two related? And yes, of course they are. Okay, all right, we'll get back. We'll do a couple of examples in the next video.